Enceladus, one of Saturn's small moons, stunned scientists. Data from the Cassini mission revealed extraordinary wonders hidden beneath its thick ice shell. Rather than being an inactive ball of ice, Enceladus erupts from fractures at its south pole, blasting enormous plumes of material straight into space. Analysis of samples collected from these plumes revealed the presence of organic compounds, chemical elements, and ultrafine silica particles, essential ingredients for life. Could there be an active ocean beneath this thick layer of ice? For the first time in human history, we directly accessed and analyzed material from an ocean beyond Earth without the need for a complex landing mission. Enceladus was never intended to be a primary target of the Cassini mission. Yet this unexpected discovery reshaped the way we search for life in the universe. On Saturn's icy moons, the true mystery does not lie on the surface, but deep below it. And Enceladus was the first to open that door. When the Cassini spacecraft flew past Enceladus, it was regarded as nothing more than a small moon, just over 500 kilometers in diameter, classified as a cold, weakly active icy moon. The instruments aboard Cassini began transmitting data that did not match any existing model. At Enceladus's south pole, where scientists expected a quiet, frozen landscape, sensors detected massive plumes of material erupting straight into space. Spectral analysis revealed a powerful, continuous mixture of water, ice, and gas escaping into the vacuum. Enceladus was not gently leaking, it was erupting. Subsequent images confirmed the presence of long parallel fractures stretching hundreds of kilometers across the South Pole. Later named the Tiger Stripes, Cassini measured temperatures along these fractures that were abnormally high. Compared to the rest of the surface, dozens of kelvins warmer than surrounding regions, for a moon as small as Enceladus. Such heat was nearly impossible to explain if it came solely from residual warmth left over from its formation more than 4.5 billion years ago. Then came the numbers that left the scientific community silent. Cassini estimated the eruption rate at between 200 and 250 kilograms of material per second. Airflow large enough to sustain Saturn's E-ring, the faint but expansive ring encircling the gas giant. Particles within the plumes reached speeds exceeding 2,000 kilometers per hour, indicating a powerful energy source pushing material beyond Enceladus's gravitational pull. These plumes were observed repeatedly during multiple flybys, proving that Enceladus is continuously active. The most important question was not the scale of the phenomenon, but its origin. Composition analysis showed that the ejected material did not come from the surface, but from deep within the Moon. This meant the ice shell was not a sealed, solid barrier. Beneath it, there had to be a reservoir of liquid water, an ocean. And that ocean was not permanently buried, it was communicating directly with space. During its passages through the Plumes, Cassini accomplished something unprecedented. It directly sampled material from an ocean beyond Earth, without landing, without drilling through ice, without ever touching the surface. Defying every prior prediction? What allows such a small moon to sustain intense activity over long periods? Defying every prior prediction? To find the answers, we must go deeper, beneath the ice shell tens of kilometers thick, into a hidden geophysical engine quietly at work. A moon just over 500 kilometers wide, far smaller than other ocean worlds like Europa or Titan, should have cooled and gone silent billions of years ago. By every classical logic, Enceladus should be a frozen, motionless block of ice, a forgotten relic from the formation of the solar system. Yet the data show the opposite, orbiting Saturn with a period of about 33 hours. Enceladus does not move alone through empty space. It is locked into a 2-to-1 gravitational resonance with Dione, a larger moon on a more distant orbit. Every time Enceladus completes 2 orbits around Saturn, Dione completes exactly 1. This forced synchronization prevents Enceladus's orbit from ever becoming perfectly circular. As Enceladus moves closer to Saturn, the gas giant's immense gravity stretches the moon's entire structure. As it moves farther away, that pull weakens. This cycle of compression and relaxation repeats continuously, tens of thousands of times each year. This is tidal force, not acting on a surface ocean like on Earth, but deep within Enceladus itself. The rocky core of Enceladus is constantly flexed. Microscopic deformations within the silicate rock generate internal friction, and that friction produces heat. This heat does not appear in dramatic explosions, but accumulates slowly and steadily over millions and billions of years. Measurements of the gravitational field, tiny changes in orbital motion, and thermal emission data concentrated at the South Pole all indicate that Enceladus is releasing more energy than can be explained by natural radioactive decay within its rocky core alone. From this evidence, scientists began reconstructing Enceladus as a layered world. At its center lies a silicate-rich rocky core. Surrounding it is a salty liquid ocean. Capped above by an ice shell, roughly 30 to 40 kilometers thick. What is astonishing is not only the existence of this ocean, but its scale. Many models suggest it may be nearly global, rather than confined solely to the polar regions. This ocean does not freeze solid for two reasons. First, heat from the rocky core is continuously transferred into the water through direct contact between rock and ocean. Second, tidal forces prevent the overlying ice shell from ever reaching complete thermal equilibrium. In regions experiencing greater stress, especially near the South Pole, the ice is thinner, allowing heat to escape more easily. This asymmetry explains why geothermal activity is so strongly concentrated in one hemisphere for decades. Science assumed that only sufficiently large celestial bodies could retain heat over long periods of time. Enceladus proves that size is not an absolute determining factor. It does not survive through stability, but through constant tension. Being pulled back and forth between Saturn and Dione is precisely what keeps it alive. If life exists within this ocean, it would be life born of pressure, deformation, and motion, not of quiet equilibrium. Thermal models showed that if Enceladus were to escape its resonance with Dione, its subsurface ocean would freeze over a relatively short span on cosmic timescales. Geological activity would cease, and the moon would become a dead block of ice, exactly as once assumed. At a deeper level, Enceladus forces us to expand our definition of a living world. It does not require sunlight, a warm surface, or a thick atmosphere. It needs only liquid water, continuous energy, and time. Together, these three elements create an environment that cannot be ignored in any serious discussion of life beyond Earth. But is this ocean isolated? If liquid water were permanently trapped beneath tens of kilometers of ice, direct study would be nearly impossible. Yet, if natural pathways exist that allow the ocean to communicate with the outside world, then Enceladus is not merely an ocean world. It is an open window. Beneath ice layers tens, even hundreds of kilometers thick. Liquid water, if it exists at all, has long been considered a secret permanently sealed away. Every exploration scenario runs into the same technical wall. Deep drilling, extreme risk, enormous cost, and a near certain chance of failure. Enceladus shattered that logic in the boldest way imaginable. At Enceladus's south pole, the tiger stripe fractures are not merely geological cracks. They are conduits piercing the ice, directly linking the subsurface ocean to the vacuum of space above. Combined data from high-resolution imaging, thermal maps, and ice structure models reveal that in this region, the ice shell is significantly thinner than the global average. Only a few tens of kilometers, and is subjected to continuous tidal stress. This is precisely what allows the fractures to remain active over long periods, rather than freezing shut like ordinary cracks. The crucial point lies not in the shape of these fractures, but in their consequences. Enceladus's ocean is not isolated. It participates in a dynamic cycle of material exchange. With liquid water, dissolved salts, mineral particles, and gases forced upward through the fractures and released into space. Tiny ice grains, gas molecules, and salts ejected into space carry with them the chemical fingerprints of the environment where they formed. Cassini exploited this reality in an unprecedented way. The spacecraft conducted multiple flybys directly through the plumes at extremely low altitudes, just tens of kilometers above the surface, instead of drilling or landing. Its scientific instruments allowed material from Enceladus to collide with them naturally. For the first time in history, humanity directly sampled an extraterrestrial ocean. Not through inference or theoretical intermediaries. This fundamentally changes how we assess the biological potential of icy worlds. A sealed ocean is a closed system, difficult to access, difficult to verify, and easily sidelined in long-term exploration strategies. In contrast, an ocean that exchanges material with its surroundings becomes a living scientific target. Where chemical and geophysical processes do not merely exist, but leave observable traces. Here, Enceladus sets a new standard. Not all ocean worlds are equal. scientific value lies not only in the presence of liquid water, but in access to information. Because these plumes exist, if life inhabits Enceladus's ocean, it is not completely hidden. Molecules, complex chemical structures, and even potential biosignatures may already have been, may still be, carried outward with the escaping material. This means that life, if it exists, is not confined solely to the world where it arose, but may leave imprints beyond its own boundaries. At a deeper level, Enceladus forces us to rethink how life interacts with the universe. On Earth, life is largely shielded by an atmosphere and a magnetic field, but on Enceladus, if life exists, it inhabits an environment where the ocean and space are not fully separated. From a strategic perspective, this discovery has completely reordered priorities and future exploration plans. It represents a direct point of contact between humanity and an extraterrestrial environment with exceptionally high biological potential. If material from the ocean has already been exposed, then what exactly does that material contain? Which molecules are being carried up from depths tens of kilometers below the ice? And most importantly, could they hold the first clues to life beyond Earth? When Cassini flew through the streams of material erupting from Enceladus, it did not see life, nor did it capture images of living organisms, but it found an environment where life could exist. In scientific terms, this meant mass spectra, ion analysis, and cold, precise graphs. But behind those numbers lay a story that reshaped how we understand life in the universe. The dominant component in the sampled material was water, not simple vapor from sublimating ice, but water carrying the signature of a true ocean. Cassini detected water mixed with dissolved salts, indicating that this was not newly formed surface water, but water that had existed for a long time, interacting with rock and minerals in a stable environment. This was an ocean that did not appear briefly, but one that had persisted long enough to establish chemical equilibrium. Alongside water were carbon dioxide and methane. These are simple carbon-based molecules. Yet their significance is fundamental. Carbon is the backbone of organic chemistry, and its presence in multiple oxidation states shows that Enceladus is not a chemically poor or static system. On the contrary, it points to an environment where chemical reactions are ongoing, where carbon is redistributed and transformed, a hallmark of potentially biological systems. Cassini also detected nitrogen, an element often overlooked but critically important. Nitrogen is a core component of amino acids, nucleotides, and proteins. In nature, nitrogen does not remain in reactive forms easily without stable chemical cycles. Its presence in the plume suggests that Enceladus's ocean is not merely water and rock, but a chemically complex environment where essential elements are accumulated and cycled. The turning point came with a small molecule of enormous significance, molecular hydrogen. Cassini measured concentrations of hydrogen-2 far higher than could be explained by surface physical processes or radiation-driven ice breakdown. The most plausible source of this molecular hydrogen is hydrothermal reactions between water and rock, similar to the process of serpentization on Earth. When water penetrates hot silicate minerals within a rocky core, chemical reactions occur that release molecular hydrogen. On Earth, hydrogen from deep-sea hydrothermal vents provides energy for ecosystems that do not depend on sunlight. Cassini did not detect organisms, but it did detect free chemical energy, the very thing life can exploit. In biology, energy is not only heat or light, it is the ability to create chemical gradients. Molecular hydrogen, when combined with carbon dioxide, can power reactions that build complex organic compounds. This is the foundation of chemosynthesis, a form of metabolism that existed on Earth very early, even before photosynthesis emerged. The case became even more compelling when Cassini detected nanoscale silica particles in the ejected material. These particles cannot form in cold, static environments. Studies indicate they most likely form when hot. Mineral-rich water interacts with rock at temperatures above 90 degrees Celsius, then cools rapidly as it rises. This provides strong, though indirect, evidence for active hydrothermal systems on the seafloor of Enceladus's ocean. Taken together, the data show that Enceladus possesses the three core ingredients of a potentially habitable environment. Liquid water that is stable and long-lived. A continuous energy source independent of sunlight. And rich chemistry that includes elements and molecules essential for life. None of these conditions is rare on its own. but their coexistence within a single system, on a small moon more than 1 billion kilometers from Earth, has shaken long-held assumptions. Life is no longer tightly bound to planets, to sunlight, or to warm surfaces. It can exist in darkness as long as the chemistry is right. Still, science does not allow for hasty conclusions. Cassini did not detect direct biosignatures. There were no cells, no clear biological structures, no indisputable evidence. What we have is potential, but potential backed by solid experimental data. And in science, potential confirmed by physics and chemistry is often more profound than a single isolated discovery. What Cassini revealed here has become a template for re-evaluating the entire Saturn system. If a small moon like Enceladus can host such a chemically rich and promising environment, then what might other icy worlds around Saturn be hiding? Not just Enceladus, but a cluster of ocean worlds around Saturn. Enceladus does not stand alone. It is merely the first piece of evidence suggesting that the Saturnian system may be a gathering place for multiple ocean worlds, each expressing a different manifestation of the same physical principle. Liquid water can exist in places we once believed to be impossible. The clearest and largest example is Titan, with a diameter of approximately 5,150 kilometers. Titan is larger than the planet Mercury and is the only moon in the solar system with a dense atmosphere, a surface pressure higher than Earth's, and a composition dominated by nitrogen. For decades, Titan has fascinated scientists with its lakes and seas of liquid methane on the surface. A world that resembles early Earth in appearance, but operates under an entirely different chemistry. However, gravity data and rotational oscillations measured by Cassini reveal that Titan's true story lies far deeper beneath its surface. Precise measurements indicate that Titan harbors a subsurface salty ocean buried beneath hundreds of kilometers of ice. This ocean likely contains ammonia, which lowers the freezing point and helps maintain a liquid state over long timescales. If Enceladus represents open oceans where material can escape into space, then Titan represents fully shielded oceans, stable, deep, and isolated from the surface. This opens a thought-provoking possibility. Life, if it exists, may not need to interact with space or the surface to maintain its stability. Titan also demonstrates that the diversity of ocean worlds is not defined by water alone, but by the chemistry surrounding it. On Titan's surface, photochemical reactions produce complex organic molecules, chemical precursors of life. Below, the salty ocean exists in complete darkness. These two environments are largely separated, but if any mechanism of material exchange has occurred between them over Titan's history, the moon could represent one of the most complex natural laboratories the universe has ever produced. Less visually striking than Titan, yet rich in dynamical significance, is Dione. For many years, Dione was regarded as an old, inactive, and unremarkable icy moon. However, data from Cassini show that Dione responds to Saturn's changing magnetic field in a way that can only be explained by the presence of a conductive layer within its interior. The most plausible explanation for this conductive layer is a subsurface salty ocean beneath a thick shell of ice. What makes Dione particularly compelling is not only the possibility of an ocean, but its orbital connection with Enceladus. The two moons maintain a 2-to-1 gravitational resonance, meaning their thermal and energetic histories are not entirely independent. If Enceladus was awakened by tidal forces, then Dione may have experienced, or may still be experiencing, similar cycles of internal activity, even though its surface expression is far more subdued. Dione reminds us that surface silence does not equate to internal emptiness. Then there is Mimas, which directly challenges long-held assumptions. Small, heavily cratered, and long considered a rigid block of ice, almost entirely geophysically dead. There are no plumes, no surface activity, and no obvious thermal anomalies. Precisely for this reason, newly published models from 2023 to 2024 were deeply unsettling. Mimas suggests that the solar system may host many invisible oceans, waiting to be revealed through more refined methods of detection. These oceans may have existed for hundreds of millions or even billions of years, entirely unaware of our existence. From the undeniable data returned by the Cassini spacecraft, the truth has become clear. Enceladus, Saturn's small moon, has forced science to revise its criteria for the search for life. its water-rich plumes. Laden with salts and organic compounds provide concrete evidence that the necessary energy and chemistry can exist deep beneath an icy shell, entirely independent of a large planet or direct sunlight from the sun. This represents a profound paradigm shift. If life emerges there, it would arise in darkness, sustained solely by tidal energy and the appropriate physical and chemical conditions of a subsurface ocean. Enceladus is not merely a celestial body, it is a scientific proof of concept, showing that life may be far more widespread than we once dared to imagine. Although Enceladus cannot yet answer the ultimate question, are we alone in the universe? It has transformed that question from a philosophical hypothesis into a serious, testable scientific problem. Within its quiet yet promising hidden ocean, the universe seems to whisper of an entirely new frontier of exploration. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.